All right, physics students, we have to make a change because I don't have a whiteboard at my house, so I'm going to do the physics short lectures by using a pen. So here we go. We're going to start on chapter 10, chapter 9, And chapter 9 has to do with work and energy. All right, so up until now, at least the last test, covered forces. And we talked about how forces can create an acceleration. Now we're also going to do work. And work is the ability that a force has to make something occur. Okay, and what occurs depends on what the situation is. But we define work as W, and it's technically the integral of force dot dx. Okay, which is kind of confusing because this looks like multiplication, but it's not. This is what's called a dot product. It's for two vectors because both these are vectors. And those vectors interact in a special way. So what we really do is if you have a constant force, then you can pull the force outside. The integral, you integrate dx, you just get x, all right? But it's a dot product, so you have to treat it differently. So what it really means is for a constant force, it's the force dot the distance that you travel, or the displacement, okay? Because it's a vector quantity, it's an actual arrow. But we want, in our class, we're going to write this as F times d, the magnitude of both of those, times the cosine of theta, where theta is the angle between the force and the displacement vector. Okay, what that means is if a object moves in a displacement vector d, but you apply a force in this direction while it's moving, the angle is the angle between the two forces. So the angle is never greater than 180 degrees. Okay? Now work can be both positive or negative, but that has nothing to do with direction. This is what's confusing. Is usually we say, oh, positives to the right, negatives to the left. It's not the case with work. Work, if it's positive at work, it means that the force is in the same direction as the displacement. If it's negative work, it's in the opposite direction. For example, if something was moving this way, but the force was applied here, the angle is here, this is the force, right here, then the negative work occurs here. Work is less than 0, work is greater than 0. Because the force is in a direction opposite the displacement. Notice that the cosine of theta, you could think of this as actually just taking components here. If we took force and we broke it into two components, you could have one going this way and one going this way. This would be F sine theta here, and this would be F cosine theta. So what this really is saying, and the dot product says, is that we only compare, because this is F cosine theta, we only care about the force in the direction of the displacement. The force perpendicular to displacement does no work. Why? Because if you have a force this way, and your displacement is this way, that angle there is 90 degrees. But the cosine of 90 degrees is 0, so you do no work. So any force that's perpendicular to the displacement vector does no work. Now, if something's moving with the velocity is the displacement vector, because that's the direction it's moving. Okay? And another thing we have, we're going to talk about kinetic energy. Because kinetic energy and work are related. Now kinetic energy, we usually write it as K or KE, 1/2 mv squared. So what it says is if you have a velocity, then you have a certain amount of energy. And we know that things that are moving have energy, and we can change that energy into something else. If you're moving along a flat road and you have a certain amount of speed, it'll get you up a hill. And you're changing this kinetic energy into potential energy. If you have no velocity, you won't get up the hill. So you have to have that energy. So you already have that energy. Well, the reason that work and kinetic energy are related is that work is equal to the change in kinetic energy. Meaning that and I should say the net work, remember net means the sum of all the work. Because more often than not, you have more than one force, so you got more than one work on an object at a given time. So the net force is going to be change in kinetic energy, which remember means kinetic energy final minus kinetic energy initial. Or in this case, it's going to be 1/2 mv final squared minus 1/2 mv initial squared. Okay? And it's always final minus initial. Now, look at it this way, if your final velocity is less than your initial velocity, that means you were slowing down. Well, if that's the case here, then the final velocity is less than the initial velocity. The work's going to end up being negative because this term is going to be bigger than that one. So whenever you're slowing down, you have negative work. Okay? If you have positive work, you're speeding up. It doesn't say anything about going right, left, up, or down. All it just says is that it's accelerating or speeding up if you have positive work. Which makes total sense because here we're saying if it's doing positive work, the force has to be in the direction of the distance. The net force gives you acceleration. The acceleration is in the direction of the displacement, meaning the velocity. So if the acceleration is in the direction of the velocity, you're speeding up. We learned that way back in chapter 2 or 3, that if the acceleration and velocity are going the same direction, you speed up. If they're going opposite, you slow down. That's just expanded upon when you do work. Okay? There's one more energy I want to talk about. We're going to have what we call gravitational potential energy. In gravitational potential energy, we usually write it as U, because U means potential, and sometimes you put a G down here for gravitational potential, because there's different kinds of potential energy. And it is equal to mg times h, where h is the height. Okay, so if you move something up a ramp, so there's a ball going up a ramp or a box going up a ramp, height is h is always a perpendicular measure. It's always measure in the direction of gravity. Okay, it's not the length you travel, it's the height that matters. And for the potential energy, you can set 0 anywhere you want, where that is convenient. For most problems, what you find is the easiest thing to do is to set the lowest point to 0 potential energy. Then your potential energy is always going to be a positive value. But the physics works fine no matter how you set it. Okay? All right. Basically, that is how work does. So I'm going to end this here. Well, I'm going to add more to this later. But right now we'll start here and we'll do a couple of problems. I'll have some problems listed for you to do, because the only way you get good at this is doing problems. All right. Mostly what you're going to do is this. Remember, be careful of the signs. Make sure you know this, 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 and this. Those are the main things we're going to be using right now. All right, here we go.